I'm beginning part 3 with the third, and not the last, but at least nearing the end of the vintage radio workbench that I'm putting together with this ICO model 950 resistance capacitance bridge. Now, what this unit does is it measures resistance and capacitance. It also measures leakage of capacitors. It'll work with everything from, I think, around 10 picofarads, used to be called microfarads, all the way up to, I don't really remember, but a couple of hundred microfarads. It also has a comparator function that I'll talk about at the end. But basically, the way this unit works is you attach a capacitor over here, or a resistor, and then you rotate this dial until the eye tube is at maximum open, and then you read the dial to get the capacitance or resistance measurement. Now you'll notice here it says resistance, capacitance. The outside scale is for either resistance in black or capacitance in red on the inside. Then it also has an expanded scale, which I'll talk about a little bit, and ratio. And ratio is the thing I'd like to show you near the end. Now, I'm hoping this will be a little bit easier restoration than that signal tracer, which required virtually an entire recap. Almost every capacitor in that was leaky and had to be replaced, as you may remember. I'm hoping this one will go a little better. But the first thing I'm going to do is measure the voltage on the output here and see although the control here says it will go to 500 volts, I don't think so. I've never seen one of these that could actually put out 500 volts, and I used one of these. In fact, the shop I worked in had 2 of these, and neither one of them would put out much more than about 450 volts. So I'll be surprised if I get more than that out of this one. So at any rate, let's take a look at the insides and see whether this is going to require a lot of restoration or maybe just a little. Here is the back side, and it has a single tube, a 6x5, not counting the magic eye tube, which we'll talk about in a second. Power transformer. This is the balance pot. This is the voltage pot, that is the potentiometer that adjusts the leakage voltage for the electrolytics. It has a number of ranges, and I'll talk about those, and I'll give it a little bit of an accuracy test after I get it working. But the first thing I want to do is bring it up on the variac and see if it will actually work, and if so, whether it needs any new capacitors or resistors or anything of that sort. I've plugged it into the Syncor variable isolation transformer. I shouldn't call it a variac. A variac is a trade name, and technically using a trade name is incorrect. You should use the correct name, which in this case I'll just call it a variable transformer. And let's turn the unit on, and then turn the voltage down on the Syncor transformer. And I've got it set to the current measurement here. So what I'm going to do is slowly start bringing the voltage up. We'll stop about there, and I'll look to see if I'm getting any light on the filament. I don't see any yet. So we'll come up a little bit further. Okay, now I do see the filament in the 6X5 starting to glow a little bit. So we'll wait a little longer. What I'm waiting for is for the filament, since, oh, well, there's some good news. The eye tube is starting to come alive. So we'll go up a little further on the Syncor, maybe about there, and check that voltage. That's at about 95 volts. It's still not drawing very much current. So let's go up a little higher, maybe about right there, which is, well, let's go to 117 volts. That's sort of a standard. 117 volts, and very little current being drawn. Well, the good news is the eye tube is on. What I'm going to do next is measure the test voltage across these terminals. I've attached this digital voltmeter to the terminals there, and I have the switch set in the electrolytic test position. And now we're going to start turning the voltage up here. See how much voltage we can get. That's set on the front to 250. Notice it's only really 213 volts. And as I suspected, this was common. This was just more marketing hype than anything. These bridges, as far as I remember, don't ever put out a full 500 volts. But let's go all the way to the max and see how much it will put out. Well, 426 volts. That's pretty respectable. Not 500, but certainly adequate for most of the radios of the day. Now, there are a few radios that have 450 or even 500 volt capacitors in them. But for 99% of the radios made in the 30s, 40s, 50s, and 60s, this would certainly be enough voltage to test them. But there's a lesson here. Don't let the numbers on the dial here fool you. They're not very accurate. Let's set it to 300 and see what it actually reads, 252 volts. So, well, at any rate, I'm happy that the unit seems to power up, that at least it does put out reasonable voltage for testing electrolytics. And so the next thing we're going to do is test the actual bridge circuit. But before we do that, it might be a good idea to take a look at bridge circuits in general, just in case you haven't seen them, so you'll understand how this unit works. I've drawn this bridge circuit, just a kind of a sketch. The basic idea of a bridge circuit is you create a diamond pattern out of some components. In this case, I'm showing them as resistors. One of the components is the unknown. Another one is something that's adjustable. So in this case, if we were measuring this resistor, what we try to do is to set the ratio of these two resistors to exactly the same as the ratio of these two resistors. In other words, if you think about Ohm's law, let's suppose for the moment that all of these resistors are exactly the same value. It doesn't matter what value, just all the same value. If we apply a voltage at the top and the bottom, if these are all exactly the same value, then the voltage here will be half of the voltage across the total. Just two resistors. We're tapping at the midpoint. Similarly, the voltage on this side is also going to be half of the applied voltage. So the meter is going to read 0. Now, let's suppose that instead of this being a DC voltage, this is an AC voltage. Well, same thing will be true. As long as this bridge is balanced, in other words, the voltage division on this side is equal to the same ratio as the voltage division on this side, the meter will read 0. Now, in the ICO, this is actually a seen eye tube, or a magic eye tube, I guess is what they call it. It's a 1629. But for now, we'll think of it like a meter. The difference is that the way they have arranged the circuit in the ICO, the I tube opens to its maximum when it has no voltage applied to it. So when the bridge is balanced, the I is fully open. Now, what's interesting about these bridge circuits is you don't have to just use resistors. Suppose you had equal capacitors here, 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 and here. In that case, if you applied an AC voltage, half of the applied voltage would be here and half the applied voltage were here. So if the indicator could detect an AC voltage, it would see 0 volts from here to here. Now, if the bridge were not balanced, in other words, if this suppose these two components are equal exactly the same value, and suppose you pick a resistor here that is exactly, or adjust this to exactly that value. It doesn't matter whether that's a resistor or a capacitor or an inductor. As long as this component is the same as this component, the bridge will be balanced and the I will be open all the way. Now, perhaps when we get to the end here, if I have a little time left, I'll show you you can do this sort of thing to compare things. In other words, instead of having an unknown and a variable, what you can do is you can actually use one of these as a reference and adjust until the reference is exactly equal or some ratio of this value. And we'll talk about that a little bit more. For now, let's get on with checking the operation of the ICO resistance capacitance bridge. I've attached a 0.1 microfarad metal film capacitor over here. We're going to set the range switch to the 0.1 to 50 microfarad position. And to make it a little easier to see the I tube, I'm going to move in on that. I hope this is going to work in this camera. Let's now rotate, looking for an opening of the tube. It should be well, I don't get any. So maybe this is not working. Let me check my settings. Okay, what I've done is gone to the next lower range. And let's see if we can see. Yeah, I think you can see that eye opening. And you may or may not be able to see the reading at that point. It's just above 0.1. This is where it should be right here, which would be 0.1 microfarad. So this one is showing just a little less than 0.1. This let's see, that would be 0.05 right there. And this is 0.1 here. And let's see where it exactly balances, or is at maximum open. It's right there. So this particular capacitor is reading just slightly under 0.1 microfarad, but more than 0.09. So let's try a little bigger capacitor, maybe a 10 microfarad or something like that. I have now attached a 15 microfarad. I'll show you in a second. I've reset the range switch to the 0.1 to 50. I'm sorry, the 0.1 to 50 microfarad position. And here is the capacitor. So now let's see if we can balance the I tube. Once again, I'll zero in on that. Okay, now let's take a look at the reading. And this would be 20, and that's 10 down there. So 15 should be right in the middle, and this one reads just about perfect, right on 15 microfarads. Let's now test this. This is a 350 volt capacitor. So let's go over to the electrolytic test position. And you'll notice that the eye is open. Now what we will do is we will start applying voltage, and watch what happens. You see it? We're going to go up to 250 volts. And what happens, this is with 0 volts. What happens when you apply the voltage is the capacitor first, or the eye closes, showing the capacitor is charging. Then as the capacitor reaches full charge, the eye opens again. Let's take a look at that again. This time I'm just going to switch the switch. So we're going to switch it to the electrolytic position. It should start out closed and then open. And it does. Okay, now I'm testing that at 250 volts roughly, maybe 220 volts. As you saw earlier, I have the knob set at 250, but as we saw earlier, that's really a little lower than that in practice. Okay, well, let's try a pretty large capacitor now near the top end. Okay, now I've set this. It's a 470 microfarad capacitor, and this would be 500. It's showing just slightly above 500 microfarads, which is a little off. By the way, I am comparing these capacitors to the Syncor at the same time, the LC102, just to see how accurate this RC bridge is. It's close, but it's not real exact. This particular capacitor is very close to 470 on the Syncor. Now, the Syncor hasn't been calibrated in a while, so I can't guarantee that it's any more accurate actually than this ICO. But the reason that I say I depend on the Syncor a little more is I've used it a lot over the years. It has always seemed to be pretty accurate. So I'm guessing that this bridge is reading a little bit high on this highest capacitance range. Well, now let's go over and test. This is only a 50 volt capacitor, so we're going to have to be pretty careful. We'll set it to where it reads 50 volts and see if it will charge. Well, it's coming open. Yeah, it does seem to be charging up okay. So it is a good capacitor, at least at 50 volts. All right, well, that pretty much finishes the testing of this. I will test the resistor function, but generally if the capacitor function works, the resistor function does too, because it's basically the same thing. And then what I'm going to try to do is to set up to do one last little thing with this bridge that might be of interest. I don't know how this is going to show up on the camera because I've been having trouble getting enough contrast on the iTube. But what I have set up here is what is called the comparator mode. In other words, I'm using the bridge as a comparator between two impedances. In both cases, these are Radio Shack transformers. They're generally power transformers. That is usually the on one side, in fact this one is wired for to be plugged into 110 volts. On the other side, by the way, the transformers produce 24 volts total, or 24 volts center tapped, in other words 12 volts either side. They're basically the same transformer. You'll see the one on the right's a little bigger than this one. They're both rated at 2 amps though, so they're roughly comparable transformers. I am terminating the secondary with a 1K resistor using a resistance box on this side. Similarly, this one is terminated with a 1K resistor. You'll notice that this one, the primary, is connected to the comparator terminals. This one, the primary, is connected to the test terminals. So what I'm going to try to do now is to zero in on the I-tube, and let me show you what happens as you rotate the balance control. Once again, I'm not sure if this is going to show up. I'm rotating the control now. Right there is the maximum. It's just not showing up on the camera, but take my word for it, the eye is showing an open. Now let's look over at the dial, and you'll see that the inner dial reads ratio right here. And if you follow that around up to the place where this is located, a 1-to-1 ratio would be right here. So if these two transformers were identical, in other words, exactly the same number of turns in the primary and turns in the secondary with exactly the same core and so on, and they are both terminated in the same resistance, in this case 1K, then this should be sitting at the center point. Now, the reason that I show this is I've seen people trying to build amplifiers, particularly tube amplifiers, where the output transformers need to be matched. That is, especially on a push-pull stage, you need to match one side versus the other side of a push-pull transformer. And by using a comparator mode like this, you can actually determine how closely matched two transformers are to each other. Once again, let me show you. If you, in fact, had two matched transformers, this knob would be sitting right there when you got maximum I-tube. In this particular case, these two transformers are not exactly matched. And I get a ratio of, well, let me get some more light on there so maybe I can see what it is. This would be 0.5 to 1, this would be 0.6, so between 0.6 and 0.7 to 1. If they were perfectly matched, they'd be 1 to 1. And I show this because a lot of people are not aware of the fact that a bridge like this, any bridge, can be used to do a variety of things, including to compare two, in this case, transformers. You can think of them as just inductors, because once you terminate the secondary, the primary just looks like an inductor. So you're comparing two inductors using a bridge. So I hope that's interesting enough to some people to perhaps provoke some conversation, at least, on using these. I have used comparator or bridges to compare output transformers before. So suppose you have a bunch of output transformers in your junk box and you're trying to find two that are as close to each other as possible. Well, this is the best way to do it. Furthermore, if you're trying to figure out what the correct terminating impedance is, you can also use a similar method I won't get into here. But I realize this is a digression from the basic idea of a radio workbench for vintage radios, but nonetheless I thought it might be interesting. So what I'm going to do now is bundle up this resistance capacitance bridge, put it back in the in its box, but before I do, I want to show you one more little thing as kind of an aside. Here is the box, or the case, that this unit fits into, and you may notice that a rather unusual item on the inside there. It's the handle. What I've done is I have reversed the handle so that the top of the unit is flat. In other words, I took the handle that used to sit up here and I put it on the inside. I've also done that with the other two pieces of ICO equipment. The reason I've done that will become obvious when I start trying to fit these into shells. Now this is a trick that I saw, gosh, 50 years ago, people using, particularly where they're going to be putting this equipment onto the shelves of a workbench. Kind of like the equipment up there, where what you want is the minimum space at the top so that you can put the maximum number of pieces of equipment onto a workbench. I'll show you that when we get everything put together in the final workshop configuration. And here you see the assembled vintage radio workbench with the three pieces of ICO gear on the bottom. And I think you can see now why I turned those handles inside. It allows you to put them in tighter spaces like this and give you a little more room on top. The only thing that I didn't include in the restoration process was this RCA voltomist. I actually restored that some years ago. The big problem with these is you need to make sure that you remove the batteries that are inside and clean any corrosion. I don't use the batteries anymore in these because if you leave them in there and they corrode, it'll pretty much ruin the whole meter. So it's better to use something else to do resistance measurements and just leave the battery out. At any rate, I hope you've enjoyed this series on assembling and restoring the equipment for a vintage radio workbench. I may add a few items to this in the future, including a variable isolation transformer in place of that variable but not isolation transformer that you see over there. But for the present, I think I'm going to call this a finished project and wish everyone a nice day.